Okay. Good morning, everyone. Welcome to week 10 of the NPTEL course on linear algebra through geometry. My name is Babya. I'm a PMRF scholar from IIT Madras. Okay. Okay. Now, let's look at the topics. In the previous session, we had covered topics regarding the four fundamental subspaces, right? We looked at the row space, the column space, the row
Yes.
space, the column space, the left null space, and the null space, right? So this time we are taking a deeper dive into what is called the least square solutions, okay? And we had a brief look at least square solutions, but I deliberately did not do it because it was coming up in the later section in a more detailed fashion, okay? So in the lectures you may have seen the approach. So what is least square solutions? So you have what are called inconsistent systems, right? So what does inconsistent system mean?
So
Yeah.
would it be possible for you to give a very brief review or the recap of those four spaces?
Oh yeah,
Uh,
sure.
yeah.
Okay, before I do this then, okay, so the four fundamental subspaces, okay. So what you the best way to look at it is categorize them into two parts, okay, and they are quite similar in that regard, that you look at the column view and the row view, okay. So what does column view mean? So the first type of subspace is the column space, okay. So the column space is just the vector which is spanned by the columns, okay. So if I have let's say this is 1 2 3 4 5 6, and let's say that's it, 1 2 3 4 5 6, then okay, column space of A is the space spanned by the vectors 1 2 3 and 4 5 6, okay. Now why are we interested in column space? Well, um, everything that we are working on up till now this point is mostly to deal with column space only, okay. In a sense that what about solving a system of linear equations, right? What about solving a system of linear equations? How do we interpret ax equals some b? Is that if this is my a given, okay, and x is, let's say, x1 x2, then it means that 1x plus 4x, right? 1x plus 4x, not 4x, 4y equals b1, um, 2x plus 5y equals b2, and 3x plus 6y equals b3, right? If this is the system given, and equivalently I can group these x's and y's together and just keep 1 plus here and say this, right?
Yes.
Right. So and this can also be grouped, b can also be grouped together like this. And now the question rather becomes, what is that combination of x, what is that combination of the vectors 1 2 3 and 4 5 6? What is that linear combination that gives the vector b1 b2 b3, correct?
Yes.
Now why is that interesting? Also that um, the other way to interpret it is I have these vectors 1, 2, 3, and 4, 5, 6. Okay, I have these two vectors 1, 2, 3, and 4, 5, 6. Okay, but there is a slight delay, I think. Yeah, okay. 1, 2, 3, and 4, 5, 6. Now I'm rather asking the question that B1, B2, B3 is here. Okay. I'm asking the question, okay, that does B1, B2, B3 lie in the plane which is spanned by the vectors 1, 2, 3, and 4, 5, 6 or not? Okay. And if it lies on the plane, what is what is the means to get to it? Okay. What is the linear combination?
Yes, yes.
Okay. So, I mean, so in this sense, in this regard, we are talking about column space the whole time, right? Now that we have that, so that is the interpretation of column space. The equivalent row view, okay, is the row space. Okay, so again, let's say I have A equals 1, 4, 2, 5, 3, 6. Now what I'm talking about is the row space of A is the span of the vectors 1, 4, 2, 5, 3, 6. But okay, in other words, the rows. Okay, if I interpret them as vectors, but these are not exactly vectors because um, until now we've only been interpreting vectors in a as columns, not as rows, only as a column matrix, right?
Yes.
So we'll rather to attend to that fact. What we'll instead do is we'll say it is the span of the columns of A transpose. So why? Because A transpose becomes now 1, 4, 2, 5, 3, 6. So these rows are automatically made into column vectors. Okay, so this is a more neater way to say it.
Yes.
Okay, so the span of the columns of A transpose. So this is the row view. So whenever I talk about transpose, then you can interpret the columns to be the rows to be the columns, and therefore the span of the columns to be the row space. Okay.
But
Now,
then what about the values B1, B2, and B3? So what can we say? I mean, similar to the column view, what can we say that the linear combinations of what 1 and 4 will be
yeah,
equals to
okay.
1, and then so on? Yeah.
Yeah, we yeah. So for example, now if you do the yeah exactly. So if you do, let's say you ask the same question. Okay, what is now A transpose times X equals B? A transpose times X equals B. If you do that, okay, you'll get some interesting properties. Okay, that you are asking what is that combination of the columns 1 4 x1 plus 2 5 x2 plus 3 6 x3 equals b1 b2 b3 instead now b1 b2. Now, okay, to do this
No, but then originally we were supposed to solve a equation wherein B comprises of, I mean, three elements.
originally it
We
was
made
three elements, that's right.
we made some transformation to the A,
Huh,
and however we did not made any transformation to the B.
that's
And
right.
for the B side, the values would still be B1, B2, and B3 only.
No. I mean, see, because it doesn't work that way. For example, like if I try to transpose both sides, okay, for example, ax whole transpose equals b transpose, because originally you are saying that originally it was ax equals b, then it becomes um,
X transpose
x
A
transpose a transpose.
is equal to B transpose.
A transpose is equal to B transpose. Now, this is still fine, but you can see that A is in the right side, right? It does not mean the same thing as this.
Right, right.
So you can't get to this by doing this. So I'm saying independently, if you do A transpose times X equals B. What does
That in that case, you could have I think probably the better way. I mean, a more understandable way could be A transpose X is equal to C. It's
okay,
not.
C, yeah, okay, it's overloaded, right? It's not the same thing. It's C, okay, C1, C2, okay.
Yes.
Now you'll get some interesting properties here. Okay, to understand what happens here, we need to talk about the other fundamental subspace. Okay, so and that is the third fundamental subspace, which is called the null space. Okay, null space of A. Now, what is null space? The null space is defined to be n of A. Okay, is the set of solutions of A x equals B, equals 0. So if we force the system to be homogeneous, then all those vectors, okay, which all those vectors, oh, is the set of solutions of, yeah, all those x's, okay, which when you apply A is transformed to the zero vector. That is what is called the null space. Okay,
Yes.
okay, this is called the null space. Now, what happens is, okay, so what do you get? For example, when you look at the column space of A, okay, so okay, first thing is the null space contained in the column space of A.
So what's the question? Is the null space?
Contained in the column space of A.
So the column space of A, yes, is contained because the value of B can always be equals to 0. In
Ah,
the in the in the column space, we need to find the combinations of the vectors and making the whole right hand side is equal to B, and B could be equals to a 0.
exactly. So the null space, okay, is are those x's which when you multiply with A will render you to 0. Okay, and secondly, now comes the part where you actually relate null space and row space. Okay, the imagine the row space to be a plane. Okay, then the null space, okay, the set of solutions of Ax equals 0 is always orthogonal to the row space. Okay, so if this is the row space, this is the null space. This vector is the null space. Okay, or it can also be that, let's say you're talking about R4, okay, 4 dimensions, and maybe null space is also a plane. Then in that case, this is not a single vector, but it is a plane. Okay, and this plane is perpendicular to the row.
Why so that is null space is perpendicular to the row space? Why so?
Okay. I mean, there is a proof for that,
Okay,
but
okay, all right.
that we'll go too deep with that fact.
Okay, all
Okay,
right, yeah. I understood, yeah.
and the relation here is that now if the other, what would be the most natural question to ask after that is that, okay, so we talked about column space, we talked about the column space of the transpose, and we talked about the null space, we talked about the now the most natural thing would be to talk about the null space of the transpose. Okay, so this is what is called the left null space. Okay, this is called the left null space. Left null space is nothing but null space of A transpose. Okay.
And how this null space is going to make us understand this row space better?
Okay. So firstly, we look at null space. Okay, it's we are forcing that system to be homogeneous. Okay, so
Yes.
null space is a plane that passes through the origin. Okay, null space is we can always imagine this, right? On the null space given a vector A, we can always imagine the null space. It is just a plane which passes through the origin that satisfies A, right?
Yes, yes, yes.
So the row space will just be that plane which is perpendicular to the null space.
Oh, yes, I understood. Yeah.
Got
Fine,
it?
fine. Yes.
So the null space again is just the opposite now. So you have left null space, which is null space of A transpose. Okay, null space of A transpose, that is solutions to A transpose Y equals 0. Okay, we are
Yes.
forcing it to be homogeneous. Now the point is that the left null space is um, equal to uh, the column space perpendicular. Okay, or simply they are perpendicular to each other. Okay.
Yes.
Now another nice property is notice that when we did Gaussian elimination to find the rank, okay, we were doing row operations, right? Elementary row operations. We usually did not do column operations. We were doing row operations, and yet we found the rank. But the rank is talking about the columns, right? Rank is talking about the minimum number of columns that are required to span
Right, right.
the
But
space.
then we can make columns transformations as well. No issues.
Exactly. Exactly. You are able to do column transformations also. But of course, you're not allowed to do a mixture of them. You can't do rows and suddenly do columns and so on.
Yes.
But you can do columns from the beginning or you can do rows from the beginning. Right. It's quite surprising that you are doing column operations. It makes sense because you're just, performing linear combinations of the vectors and then finding out that, okay, some of the vectors are duplicates of the others. Right. Scalar multiples of the others.
Yes.
But the row, how does it work for the rows? I mean, because you're doing linear combinations of the rows also, and surprisingly, it's working for the column space also. Because, I mean, this is possible because uh, it is always true that the following facts are always true that the row rank is equal to the column rank.
Right, right, right.
Okay, the row rank is always equal to the column rank. And the second thing is, okay, now this is where it's interesting that oh, okay. By the way, what is row rank? What is the row rank in terms of the row space? It is simply the dimension of the row space, right? Because what is meant by the dimension of the row space? Row space is just the span of the rows of A, and dimension simply means the minimum number of the number of linear independent vectors required to span the row space. You get it?
Right. Yes, yes.
And this is the dimension of the column space. So the dimension of the column space is always equal to the dimension of the row space. Okay. And the second thing is, what about the null spaces? Okay. And this is what is called the rank nullity theorem. It says that, okay, the null space, okay, of A. sorry, the dimension of the null space of A, which is also called the nullity, okay, plus the rank, which can be either row rank or column rank, is equal to n, which is the number of columns. You get it? Okay.
Yes, yes, it is okay. Yeah.
Okay. And the dimension of the left null space plus the rank is equal to m, which is the number of rows. Okay.
Right, right. Yes.
Now, why is this interesting? Because the nullity is a measure of uh, nullity is a measure of uh, uh, the dimension, okay, of the system. Or in other words, if you have a system of equations, okay, and let's say there is a unique solution. If there is a unique solution, if there is a unique solution, it means the rank is full, right? It means the rank is full. Now, if the rank is full, that is rank is equal to n, then what is the nullity? Nullity is zero. So an alternate way to test if there is a solution, there is a unique solution, is to check whether the null space, the dimension of null space or nullity is zero.
Right, right.
Okay. So nullity is a measure of that. So the more smaller the more smaller the row space or column spaces, the larger the null space becomes. Okay. And similarly with left null space also. So this is one particular application of null space. We did another application in the previous session. Okay. Anyway, I think this is enough of an explanation,
Yes,
right?
yes, yes, yes. I could
Okay.
understand. Yeah, thanks. Yeah.
Okay, great. So let's move on to this week's content. Okay. Now this week's content talks about majorly about least square solutions. Okay, least square solution. Now, you have what are called inconsistent system of equations, right? So what is an inconsistent system of equation? Well, a system of equations where there is no solution. One simple example would be 2x plus 3y equals 8 and 4x plus 6y equals say 9. Clearly this system is inconsistent because if 2x plus 3y is 8, then 4x plus 6y would just be 8 times 2, which is 16, right? But it is inconsistent. It is 9 here. So this is inconsistent. So, in other words, no solution exists. Now, I would like to ask you to think about this question: that what would it mean geometrically for a system to be inconsistent?
So that would mean that I mean there are two parallel lines, and then on those two parallel lines, sorry, parallel lines,
Huh.
and the value for the one line,
There are two
the
parallel lines, and
and there are two parallel lines, and but then if this value is 8 and then 9, and it should have been say 16, so that would mean, and so a point which is satisfying this thing, a point which is lying on
ah,
the first line,
okay, okay,
uh, this will result into 8, and but then there are two parallel lines, so the second for over the second line, the same line is going 9.
okay, okay, right, right, right.
So but then
And what about what would be the interpretation in terms of vectors?
So vectors would mean that the I mean the vector 2 comma, oh, so that would be like 2 comma 3. Yes, I move two steps.
Huh.
Let us go to the very basic one. I move two steps right and three steps up, and I will reach to some point.
Huh.
Uh,
Okay.
and then I move four steps right and then six steps up. I will move to some other point.
Huh.
But then that point is not. I mean, so we would be having the different vectors.
That is
I
right.
mean, and the combinations, right? So, however, the second vector
Huh.
won't be just a scalar multiple of the first one. And whereas in this case, the second vector should be the scalar multiplication of the first one, and which is not the case here, I guess.
This is not the case here.
No.
So that is right. So in general, okay, in general, we can say that um, in general we can say that um, yeah, like okay, I'll talk in terms of what you were saying. So we are talking about 2x 3y 2 this vector, right? Basically, this vector forms a basis for both of these vectors,
Yes. Yes.
right? Both of these vectors, and yeah, both of these vectors, and the question is that can I reach the vector 8 9,
Right. Right.
right? So that is the question. Now what you are saying is that for this to happen, okay, for this to happen, I'll look at what is spanned by this 2 3, and then I have a line. I cannot, it is not possible to actually go to 8 9. That is what we are trying to say, because 4 plus 6y does not go there. And I mean, that is a linear equation interpretation. But here is what I want to say is, instead of thinking about it just this way, I mean, a more generalizable thought, okay, is that again, I'm asking this question. If I'm given a set of linear equations, okay, I'm thinking of this in terms of linear equations, okay, in the following column sense, okay, column sense. You were thinking in the row sense, okay. The column sense would be 2x plus 36y, okay, equals 8 9.
So that would mean that this 8 9 is not there in the column space of 2 4 and then 3 6.
Exactly. Yeah, exactly. That is the point that I'm trying to make.
Yes.
Inconsistent systems means that the column space is not sorry, the target solution is not there in the column space.
Yes.
Okay, so the geometric way to view it would be, imagine this is your coordinate space, and you have 2 4 and 3 6, which look, let's say, like this, 2 4 and let's say 3 6. Okay, now you look at the column spanned by it, this the plane spanned by it. Okay, and 8 9 is somewhere here.
Right. Yes.
Okay, so that is how you see it. So it means that no matter so checking for inconsistency means that no matter what you do, okay, no matter what you do, it is not possible to get to 8 9 doing linear combinations. And now the question is, now what can we do? We can't do anything. We can't find such a solution. So the
So
least, yeah,
so we can find a solution and which is pretty much closer to this 8 9. I mean, which is there on the boundary of this spanned plane.
right. So that is what least square solution does. Okay, I mean, since it is so bleak, the chances are so bleak. What we want to do is the closest possible approximation. So we need a closest possible approximation. Okay, and that is what least square does. Least squares method. Okay, and how does it do it? Well, what it actually calculates is the projection of 8 9 onto the plane
Yes.
spanned by 2 4 and 3 6. This distance is minimum across all the vectors on the plane, right?
Yes.
And this is perpendicular, and that is all that actually least square does. Okay, and but it's a very profound concept. Okay, even though that the simplest concept that it has is actually very simple. uh, that is what least square actually does. So I'll come to how we get to the least squares. Okay, but first I just want to do this quick small um, exercise. Okay, so here we are not talking about a plane. We just have a simple single vector. Okay. Okay. So the question says the following: in R cube, let B equals 2 3 4, and let the column space of A be spanned by the vector A equals 1 1 1. Okay.
Yes.
Now find the projection of B onto the column space of A and compute the residual vector. In other words, it is just saying find the least square solution.
Right.
Okay.
Right.
Find the least square solution. By the way, least this is not exactly the least square solution. Okay. What is the least square solution? Least square solution is a solution. Okay. Remember, what is the solution to a system of equation? It is a bunch of coefficients, right? It is a bunch of coefficients. So this is not the least square solution. Okay. If let's say least square solution is x star. Okay, let's say least square solution is x star. It is that linear combination which will lead you to this point. That linear combination that will lead to this point. So it means still you need to perform that linear combination, right? So this point, okay, let me indicate with the green, okay, which is the closest approximation, is actually a times the least square solution. Get it?
Yes. Yes.
Okay. Um, so that's what we need to do. But so let's say B is 2 3 4. So let's represent it diagrammatically. You have this coordinate space, suppose, and you have this 2 3 4. Okay, and then you have this 1 1 1. Oh, okay. And
Yes.
all you need to do actually is project 2 3 4 on 1 1. Okay, and so that particular combination will be the least square solution. And to get the projection and to get that particular solution, you need the least square solution. Anyway, but in this particular question, since we are just doing a projection of two vectors, we don't need to apply the standard least square solution. But in the background, least square solution is what we are computing. Okay. So what we need to find is the projection of the vector 2 3 4 onto the vector 1 1. Okay, and or onto the column space of 1 1 1. Okay, now what is that? Well, we already know that the projection of two vectors of u vector into v vector is nothing but the dot product of u and v, right? And the dot product of v and v times v. Hmm? And so what is uh, the dot product? So all I need to do is find the dot product of 2 3 4 times 1 1 1 divided by the dot product of 111 with itself. Okay, which is just the norm squared and times 1. Okay, this comes to 2 plus 3 plus 4 is 9 divided by this becomes 3. Yeah,
I said 3.
yeah, 3. Okay, good. And you cancel this off, then what you get is, oh, okay, and you have this 111 on the right also. Okay,
Yes.
so this projection comes to 3 comma 3 comma 3, which we can clearly see that it lies here. Okay, now, yeah, so now it is saying compute the residual vector. Okay, and the verify that the residual is orthogonal to. So now I come to this residual, the concept of residual. Okay, so what is a residual? Well, if let's say I have my plane here, okay, and I have my vector b here, okay, which I want to project orthogonally project onto the plane, which is the plane is nothing but the column space of A, right? I want to project it on the column space of A. What did I get? I got this, right? Ax star is this red vector. Okay. In this case, I did not need I did not require to do Ax star. In this case, it is nothing but the projection, or which is nothing but the projection of B onto the column space of A. Okay.
Yes.
Right. Now, what I want to do is I want to get a, a measure of how close we are to the actual solution. Okay. We want a measure for that. And what would be the best measure to do it? Well, this distance would be the best measure to do it, right?
Yes.
And that is what is called the residual. So, and how do you get to the residual? How do you get to this residual?
B minus A, like say B minus a small a in the previous example.
Ah, yeah, right. Exactly. B minus this the
B
small.
minus small a. Very small a.
Oh, no, 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 no. B minus small small a is your plane in this case. You get it, no?
In this case, it is a plane because we are taking the column space here. In the
Uh,
previous example, that used to be a single vector.
it was a single vector, but it yeah, go on.
So in that case, I mean, it would be B minus A. I mean, we were looking for that vector, and which basically gives the measure
Ah,
of the.
okay. I get what you mean. But if I do B minus A, okay. See this the projection came to 3 comma 3. So this point came to 3 3 3, right?
Yes.
Now if I do B minus A, um, which is 111, I will subtract like 111 component. I'll get here, no, and it has this distance. I mean the this vector, but it also has a component here. You get it?
Yes. But then
Huh?
that value would be, say, if it is the vector A plus X, and it should become B.
Huh?
So then, uh, yeah. But then, I mean,
No, I mean you're. I mean conceptually you are very close. Okay, we need to subtract something.
just to minimize the error kind of the thing. So, what would that residual be? Can you go slightly down in the slide? And
Yes,
yeah.
yes, yes.
So in this case,
So
if I find it,
I just want this component. But as you can see, B has a component in the left side also,
yeah,
which is actually causing you to get some extra values, which is not relevant to us. We just want this distance.
yeah,
Okay, just to give you a hint, so this is the origin, right? This is the origin.
So can we take the help of the null space something, and then we can?
I don't know if you can, but yeah, that is not required.
Yes. Okay.
But you are very close. Okay, I mean, all you need to do is observe that. I mean, the distance that b is from the origin in the horizontal component, okay, is same as the distance that this ax star is, the projection is in the horizontal component.
Yeah.
So all you need to get this vertical component is subtract that horizontal component. You get it? If I subtract this ax star, which I got from projecting it on the plane, all I'll get is the vertical component,
Yes.
right? So therefore, first what I'll do is that therefore the residual, which can be represented by the vector r, okay, is the b vector minus
Yeah.
ax, okay,
Right.
or b vector minus projection of b on that particular space, okay. Now, um, so where was I? Okay, so this is the residual. So now what do I get after doing that residual? After finding the residual, I notice that the residual will always be perpendicular to the plane, because if it is not perpendicular to the plane, it will contradict the fact that b is the shortest way to get to. Sorry, the that the least squares ax star was the shortest approximation. It is the best approximation. So it is always perpendicular.
And what is the goal? The goal is to find the x star which minimizes this entire stuff or something else.
That was a previous goal. We already know that ax star is the minimizing. Uh, uh, it is the it is the vector that minimizes the distance between b and the column space. That we've already seen.
Okay. Yes.
Now
Yes.
the goal is that I just want to see how good my approximation is. I just want to find a measure of how far I am from the actual vector b.
Yeah.
Okay, and that is measured by the norm of this, right? The length of this vector.
Correct.
So if I find the norm of the residual, okay, this is a measure of how good the approximation is. Okay, okay. So that is the use of the norm of the residual. Okay, great. And remember that it is perpendicular to the plane. Okay. So anything else I had to say? Okay, no. So so it's saying compute the residual vector, verify that the residual is indeed orthogonal to A. Okay. So this I told you, right? This it should be orthogonal to A. Now,
Yes.
yeah, because A forms the basis vector of this particular uh, uh, column space. So it should not, in fact, it is not just orthogonal to A. It should be orthogonal to every vector in the column space. Okay. And which is quite kind of obvious in this case because it's just a single line. Okay. Now, find the projection of B onto the column space, compute the residual vector. Let's compute the residual vector then. Okay. So you've got your AX star, or equivalently your projection, to be 333, and you've got your B, okay, which is the vector to be projected, is 234. So all you need to do is 234 minus 333, right? So R is equal to 234 minus 333, okay, which comes to minus 1 0, 4 minus 3 is 1. Okay. So this is your residual vector. Now let's just, for the sake of understanding, compute the norm also. What is the norm of L2 norm? We are talking about L2 norm. Oh, by the way, this is why it's called least square solution. Okay. Why do you have squares out there? Why is it called least square solution? Because you're talking about the Euclidean norm, which is also called L2 or square norm, right? Because, okay, so in terms of Euclidean norm, you get the best approximation. In terms of other norms, you may not get the best approximation. Okay.
Uh, yes, uh, but then
Yeah.
yes, maybe true. But then if we use the other norms, like say, I remember that there used to be. I forgot that there used to be a circle kind of the thing to find the approximation, and then there has to be a square kind of the thing to get the approximate solution and machine learning subject. So there is, I mean, people used to use the other some other knobs as well, and I just forgot its name.
Oh, okay.
I will tell you once I recall that thing. But yes, so it is
Yes.
true.
I
Uh,
mean,
we used
yeah,
to
I,
see
yeah.
that famous diagram wherein we draw a tangent touching the square, and then a tangent touching the corner of a square. And
Okay.
I just forgot. Then this used to be called something, some relaxation, something related to. I just forgot its name. Yeah, but
Oh,
then
okay.
there they used to use some other norm as well, I guess. But in this case, the value of the norm came out to be the square root of two.
Yeah, yeah. I mean, in this case, which is the L2 norm, but I mean, you can have all sorts of other norms. You can define your own norm. I mean, okay, I don't know about ML. I am not really exposed to the field, but like a very simple norm is L1 norm. I think
Yes,
I think ML people call it Manhattan distance or something maybe. So
yes,
L, yeah,
yes.
right. L1 norm is just you take the absolute value of the vectors v1 and v2. Okay, so the I mean, you what you do is uh, you just if you have the vector 3 4, then you just go 3 steps to the right and 4 steps above, so it just becomes 3 plus 4, which is 7. So I mean, that is the idea with which you'll go. And I do not think that least square solution would give you the optimal solution in this case. Probably not. Yeah, I'm not sure, but I mean, yeah, yeah. I mean, there are all sorts of norms that you can define there. But I, as humans, like L2 norm would be the most uh, natural norm for us to say that to approximate distances. Okay, and yeah, in this case, so we find the L2 norm of R. Okay, and which is the square root of -1 whole square plus 0 square plus 1 square, right? Which is equal to root 2. Oh, yeah, I think this is correct. I hope I didn't make a mistake on the way. Which is
Yes,
something
yes.
like 1.4.
1.4.
1 point something, right? 4, is it?
1.4. I don't remember. 1.41 probably.
Yeah,
1.4.
1.41, something
Yes.
like that. Yes. Um, okay. So that this is our. So it means that I cannot get a better value than 1.41 and so on. In some sense, it gives a lower bound. Okay.
Yes.
Now, um, we computed the residual vector. We want to verify that the residual vector is indeed orthogonal to the column space. So all I need is a candidate of the column space and do a dot product, right?
Yes. Yes.
So A itself is a candidate of the column space. Okay. So all I'll do is a dot product 101 1 minus 101, which is the oh yeah, residual, correct, dot product with a candidate of the column space, which is equal to yeah, minus 1 plus 0 plus 1, which is equal to 0. So orthogonal. So it looks like everything we did is correct. Okay, good. So now we move on to performing um, finding least squares in a more complex scenario, more complicated scenario where the plane is not just a plane, it's a line. So whether it's not just a line, it's a plane. Great. So it's saying given this A and B, find the least square solution XLS, interpret your solution geometrically. Well, interpretation I think we can understand easily, but what about least square solutions? XLS. So firstly, is this system inconsistent? Let's check that. Okay. I mean, even if it's not inconsistent, we can still find least square, but it makes sense to do it when it's inconsistent, right? So can we see it outright? 1 2 1 3 is 2. So this part looks a bit inconsistent, right? 1 2 is equal to 2 and 1 3 is also equal to 2. That would mean that 1x plus 2 y equals x plus 3y, right?
Yes, yes.
And this would either mean there is a free variable or there is some kind of inconsistency. And 2y is equal to 3y, which is clearly inconsistent,
Yes, yes. Right.
right? So, okay, I was thinking of doing Gaussian elimination, but we don't even need to do that, it seems. Okay,
Right.
so just for the sake of notes, I'll write that um, according to description, um, x plus 2y is equal to 2 and x plus 3y equals 2, which is inconsistent. Okay, so now it makes sense to find least squares. Okay, now I won't get to the proof of it. Okay, but
So, what is the relation in between finding the least square solution and having something which is inconsistent?
and having,
Because ultimately, I mean, and having an inconsistent,
oh yeah,
setup.
because see, if your solution is consistent, then you have a unique solution, right? Already. So why do you need to find the least square solution? The least square solution itself is the
Okay.
solution you already have.
Yes, yes, yes. Got
If the solution is inconsistent, it means that the vector is lying like we saw earlier. Okay, if the so, yeah, this is the case you have in case of inconsistency. You know, if it is inconsistency, and if the system is inconsistent, then it is somewhere outside. Therefore, we want to find projection.
it.
Okay,
Right. Yes,
good.
yes.
Okay. Um, so we have inconsistent. Now it makes sense. That's what I'm saying. That it makes sense to find the least square solution. Okay. Now, so how do you find it? That's so. So I'm not going to go to the proof of it because it's already done in the lectures. You can check it out if you've not seen. But the least square solution, okay, can be found out by solving the following system. Okay, and okay, let's so this is the one. A transpose A whole inverse A transpose. I think this is correct. I always get it wrong. Is equal to XLS. Okay, or X star. That's the notation we're using. X star. Okay, here also I'll write X star. Okay, and remove this. Okay. Now x star is nothing but this, and this has already been given to you. Okay, but see the you remember the projection example that we saw here, right?
Yes.
And this is just a direct application of that. I mean, it's the proof just goes in the same manner because the dot product. By the way, okay, the dot product of a column space. That's what we want to do. No, so we want to do the projection of B onto the column space of A, which would mean that I need to do a dot product of the column space of A, B and the column space of A, B and the column space of A, divided by and so on. But this and divided by the uh, column space of A, column space of A times the column space of A. And but A is a matrix, so this guy I can write it as, since vectors A B, the dot product of vectors A B can be written as uh, A transpose B, right? B transpose A, right? Right?
Uh,
Or is
yes.
it A transpose B? This is also something that confuses me.
So I have a point
Uh,
here that I mean, probably we discussed sometime in one of the sessions. Say if AX is equal to V is the thing we are looking for, then we
oh, I
multiply
see.
both sides by the transpose of A. And
If
if we are looking for say the solution of AX plus B,
uh,
and then not this one. So not this one. I mean, I was trying to interpret this the value of the x star in a slightly different way,
mm,
and which is easy to perceive, I guess. So if we are looking for ax is equal to b, and
uh,
then we multiply both the sides by a transpose. So then in the left hand side we would be having a transpose ax is equal to a transpose b,
uh,
and then to get the value of the x I take the inverse, and then becomes what, say I multiply both the sides by the inverse.
uh,
Inverse is a transpose a, so then the value of x came out to be a transpose a inverse, and that the equation which you wrote here. uh,
but why are you doing that sequence of operations?
yeah, so
Yeah,
we are doing the sequence of the operation because to find the inverse probably we require a symmetric matrix kind of a thing, and this B could not be symmetric. So to make everything symmetric, because this A transpose A would always be symmetric,
yeah, that's right.
correct? So can you write that equation here so that I would be able to explain things better?
Yeah,
Like
you're saying
AX plus B. So we are looking for AX is equal to B, and then
mm,
we multiply both the sides by A transpose. So then it becomes A transpose AX is equal to A transpose B. And now to get the value of the x, I multiply both the sides by the A transpose A inverse. So then this left hand side becomes equals to x, and the right hand side becomes equals to A transpose A inverse, and then A transpose and then B. That's the equation which you wrote here.
no, but you see, if you multiply A transpose A inverse
First,
to A transpose
A,
A,
and then
oh, okay,
x.
okay, okay. So inverse is outside.
Yes, yes. So then this the value of the x came out to be, and then you need to write b in the right hand side as well. So that I mean, yeah,
Transpose A B. So then
yes.
you
And
have x equals.
the same equation which you wrote above.
Okay, okay, okay. See, okay, okay, okay. Yeah, this is um see, this is uh see, as if, but see, if you do this directly, so what is the point that is actually transpose operation is fine. A transpose A inverse is also existing. So what is the reason here? See, because if this is always possible, then it would mean that um, your system is always consistent, right? Because you can always find the solution to x,
Uh,
right? If I
yeah,
do this sequence of operations, left multiply by transpose, which is still
but
valid.
I do not see any flaw in this calculation. Uh, but
No,
probably the problem here is something else. Problem here is something else in the sense that we do not know the precise value of x. But then you also wrote the approximate value of x. I mean, similar to this one.
exactly. So that's what. So if this is the approximate value of x, and this is only, I mean, because see, finding the value of x is not always possible, right? See,
Yeah, but
I mean, the only case when finding value of x is possible is when it is consistent. System is consistent, which means an inverse exists. So the it is only possible when x equals a inverse b,
yes, that's right.
right?
That's right.
The issue that I was pointing out was that if that is the case, then I can always compute this, right? I mean, even if this, I mean, given any system, I just compute this and I'll get the original, I mean, the accurate x, no, not an approximate x.
Right. So there might have been some flaw here then, but with which we are, I mean, unable to
Yeah,
solve.
there's
But we
something that we
just
are. Okay, so what you mean is left multiply by A transpose, which is a valid operation, and then multiply by A transpose A whole inverse on both sides. Okay, and yeah, this is associative also, so I can do this first and then um, do this inverse and then multiply. Oh, okay. I mean, this is I don't see a problem here. Okay, okay, good example. I mean, this is driving me crazy. Okay, I'll think about it. Okay,
yeah, yeah, sure, sure. Yeah,
yeah, this is a good point. Thanks. Okay, I'll think about it. We'll maybe talk about it at the end of the session or the next session. Okay.
sure, sure. Yes, yes.
Okay, great. Um, okay, but I wanted to say how this came about. Well, the proof is actually very similar. You just want to find a direct projection. So the inner product of AB is just AB transpose, right? Oh, is it AB transpose or A transpose B?
So this should be A
A
because this is
transpose B.
inner product. So A transpose B. The T should come
Ah,
in. I mean, in between. Yeah.
A transpose B. That's right, right? A transpose B. So then you therefore can write this inner product as B transpose then times column space of A, which will give you a scalar guaranteed. Oh no, this will not necessarily give you a scalar because here you have a matrix, and here below you'll definitely get a scalar column space of A times column space of A, and but you can do the same stuff here. Column space of A transpose, and in this case, instead of writing it as column space of A, you can write it as A transpose comma A times A, and then continue, and you'll get to this solution here. Okay. Now, uh, um,
I have a slight problem in the notation. So when you wrote column space of A,
ah,
would it be entire space? So uh,
A.
what should I?
A. Okay, it is enough to interpret it as A. Okay.
Yes, yes.
Okay. Great. So, okay. So that is done with. Okay. So now to find this approximate solution, I need to solve this. Okay. And to do that, okay. See, I can either compute A transpose A and do an inverse and so on, but a simpler way to do it would be left multiply by A transpose A on both sides. Right?
Yes.
So I'll simply do A transpose A times X star equals A transpose B. Okay, so you need to find two things, that is A transpose A and A transpose. Okay, so what is A transpose? 1 1 1 1 2 3 1 1 1 1 1 2 1 3 1 2 1 3 times A is 1 1 1 2 1 3 times X star is equal to A transpose again is 1 1 1 2 1 3. What is B? B is 1 2 2. Okay, great. Now what is this? This is 2 plus 3. This is 3 plus 2. Okay, so we can multiply it. And what do you have? You have 1. Oh no, 1 1 1 1 1 1. So that will be 3. Okay, then you multiply this guy, and this guy will be 1 plus 2 plus 3 is 6. Then you multiply the bottom row and first column. 1 plus 2 plus 3 is again 6. Oh, it'll be symmetric anyway. So, and here it will be 3. Is that correct? Oh, no.
It's correct. It's correct. Yeah, it's correct.
It's correct.
Yes.
Uh,
First row, first column, 1, 2, 3, and then first row, and then the second column would differ. So that value would be 1, and plus 2, 4, 4 plus 1, 5, 5 plus 9, 14 value will come somewhere.
Wait, shouldn't. Okay, I'm thinking. Wait, 1 2 3. Shouldn't this be larger? This value. 1 2 3. Shouldn't it be?
Last value would be 14. That's it. The remaining
14. That's right. Yeah,
values are correct.
14. That's right. Yeah. Okay, now it's correct. Yeah. 14 times X star is equal to. Now let's do this. This should come as a 2. So you, if just to do a sanity check, this is a 2 cross 3 vector. This is a 3 cross 1 vector. So all I should get is a 2 cross 1 vector, right? So so this is 1 plus 2.
First value is 6.
Plus 2.
No. 5.
It's 5, no?
First value is 5. Yeah.
And the second value is 1 plus 4 plus
11.
6, 11, right? Great. Okay. Okay, yeah, right, correct. Now all we need to do is solve the system of equations, right? So let's solve the system of equations. So how do you solve it? Well, we can use Gaussian elimination, or we can use substitution, anything you want. But what should be the dimension of X star?
It should be 2 into 1, 2 into 1.
2 into 1. Three cross 2. Yeah, that's correct. Correct. Okay, good. So now let's solve this equation. So one round of elimination should do it. No, 3 6 6 14 5 11. 3 6 6 14 5 11. Okay, so let's bring it to row echelon, reduced row echelon. So which is R2 minus 2R1, which is equal to 0. Sorry, 3. This is still same. 3 6 5, and this is 0. 14 minus 12 is 2. 11 minus 5 2s are 10 is 1. That's correct, right? and now all you do is divide the second column by 1. And okay, so that'll be overkill. So it just means that x2 star, okay, given that x star is equal to x1 star, x2 star, okay, x2 star is equal to 1 by 2. So, and what do you have next is 3x1 star plus 6x2 star is equal to 5. So substitute that now. So which is equal to 3x1 star plus half of this is 3 equals 5. So x1 star is equal to 2 by 3. Correct? Okay?
Yes.
Okay, good. So this is your least square solution, but what do you want? We want the closest. Okay. We want this, okay, x star, but okay, it's not mentioned in the question. But what we want is the vector that best approximates b. Great. So let's do that. Now let's apply a on it. Okay. Closest approximation is equal to ax star. Ax star, which is equal to a is what 1 1 1 2 1 3 times x star, which is 1 2 2 3 1 2. Okay, and which is equal to, see, this is 3 cross 2 and this is 2 cross 1. Right, so I'll get a 3 cross 1, which is correct. Okay, now let's do that. Okay, this is 2 by 3 plus 1 by 2, and then this is 2 by 3.
7 by 6.
Yeah.
I told you the final value is 7 by 6.
Oh, okay, great. This is 7 by 6. Okay, and then I have 2 by 3 plus 1, and then I have 2 by 3 plus 3 by 2. Right. So this is 5 by 3, and this is 2 by 3 plus 3 by 2, which is 6 here, and 3 to the 6, 4 plus 3, 9. 4 plus 9 is 13. Is that correct?
Yes, values are correct.
Okay, great. So this is what we have. So this is our least square solution. And well, interpret your solution geometrically. We've already seen what the interpretation of the solution is. Well, what we can again do is we can, at least to find out the measure, the best that we could do is so let's measure the, we need to find the norm of the residual, right? So but the residual would be 1 to 2 minus this value. Okay, 1 to 2 minus this part, which will give us just the perpendicular component, okay, which is equal to okay, 1 minus 7 by 6 would be minus 1 by 6, and this would be 2 minus 5 by 3, which is nothing but 6 minus 5, which is 1 by 3, and this is 2 minus 13 by 6, so that 12, this is minus 1 by 6. That's correct, right? Yeah. Okay. Mhm. Okay. So this is what we got, right? This is the residual. So this is the residual. Now what we can do is again multiply it with one of the candidate in the vector space, which is this 111 or 123, any of these, and what you should be getting is that um, you'll be getting 0 if you do the dot product, right? So you can try that. Uh, Also, we want to check how good our approximation is. So all we need to do is, oh, I mean, in fact, we can just do it. So we can take 111. This is definitely in the column space, right? So if I do R dot product with 111, okay, which is equal to minus 1 by 6 plus 1 by 3 minus 1 by 6, and these two will together form 1 minus 1 by 3, and so this is equal to 0. So we can see that it is indeed orthogonal to the column space. Residual is indeed orthogonal, and the norm of the residual will give us the limit to our approximation, okay, and which is equal to square root of 1 by 36 plus 1 by 9 plus 1 by 36, right? So as you can see, this is like very very small.
Square root of 1 by 6.
Square root of
1 by 6.
1 by 6. Okay, great. So is equal to 1 by root 6, which should be like a very small quantity. Oh, or is it not? Well, 1 by 6 would be something like 2 point something, right? So 1 by 2 point something, which is equal to something like 0
Yeah,
0.5.
0.5 something.
Yeah, which is almost 0 point. So yeah, this you cannot get better than this in terms of Euclidean distance. Okay, so that is something that we've understood now. Now we did that. Now quickly let's do the other one. Okay, this is a simpler one. I would say try it out yourself. It's just a matter of substitution. Okay, if it's
Okay.
okay, we'd rather go to this question, question 4. Okay, uh,
All
okay. So question 4 is an application of least squares. So in fact, least squares is kind of a popular technique in statistics. So it is used in or numerical analysis and so on. It's used in data fitting.
Yes, and this regression stuff, linear regression is all about this least square only.
Right. So
Yes, yes.
yeah. So now, now why it works is what we saw in the background. This is the reason that it actually works, because in the background you're talking about um, minimizing the distance between the subspace. So here is the question. So you have these data points 0, 1, 1, 2, 2, 2. Okay, and using the least squares method, I want to get to this fit this line y equals a plus bx. Okay, using least squares, write the system in matrix form, compute pseudo inverse. Oh, by the way, sorry, I forgot to tell you this. This value a transpose a inverse a transpose is what is called a pseudo inverse, because it is acting something like inverse, because you know that x equals a inverse b, right? But we are saying that we cannot find x. We can find something close, that is x star. We are saying x star equals the pseudo inverse, which is shown by a plus. Okay, so it's not technically an inverse. It's not literally an inverse, but it is something like a false inverse. So therefore, we call this the pseudo inverse. Okay.
Yes, yes.
Okay. So now write the system in matrix form, compute the pseudo inverse, find the least square solutions a comma b, explain the geometric interpretation of each solution. So yeah, okay.
Yes. So what would be the capital A here? Would it be that I write this equation of the line in the form of a matrix or in the form of a vector or what?
Yeah, exactly. So what would be a and b here? So to understand that, let's just do it this way. Okay. So y equals a plus bx. Okay. How do you think of it in terms of a line? Okay. So you have these data points 0, 1, 1, 2, and so on. These are not yet vectors. Okay. To us, these are not yet vectors because we are talking about lines in the coordinate setting, not a vector space setting. Right. This is the row way to view it. Right. So you have these points, which is 0, 1, 1, 2, and 2, 2. Right. And now you want to, oh, okay, 1, 2 won't lie there. 1, 2 will lie somewhere here, and 2, 2. Now you want a line that fits here. Okay. Now, and what is A? A is called the y intercept, right? So A can be something like this. This is A, and then bx. Okay, great. Now let me think of what is now in terms of this lines and these lines, okay, and points. What will be x's and y's here according to this? Okay, what will be x's and y's? Well, this is the x-axis and this is the y-axis according to the plot. So this is what x's should represent, right? The left coordinates is what x's should represent, and these are what the y coordinates should represent. Great.
Yes, yes.
So let's just for the sanity's check. Okay, let's just do that. So y can be 1, 2, 2. Okay, and is equal to a plus b is b, of course. X is now in this case 0. And here it is a plus b is 2.
B, B, X is 2B.
Oh, okay, sorry, 1b, 1b, sorry, right? Because this is the left hand side is x, and
Yes.
this will be 2b.
Right.
This is sort of how we want the line to behave, and we want one line to approximate this, right? Now, I hope you can see that if it were possible to solve this and get the values of a and b, it means that all these 3 points would pass through this line,
Correct.
right?
Correct.
For that particular a and b. But is it possible? Is the system consistent? Let's see. So this is nothing but a. Okay. Now what you're saying is a equals 1, and here what do you see? You have you substitute 1 here, then b is also equal to 1, but then a is 1 and b is 2 times 1, so 2 plus 1 should be 3, but it's 2. So it's clearly inconsistent, right? Okay, good. So now let's try to write it in terms of um, a matrix form. Okay, so what does it mean? Actually, we want to find a least square solution for this vector a, right?
Yes.
Okay, great. So let's try to do that. What we can do is let's see, we can take this to represent a, in a sense that this I can write it as 111 012 times ab, okay, is equal to 1 2 2, right? Because when I multiply, this entire thing will get multiplied with a plus a b component,
Yes.
correct? Now all that is left is to solve the system of linear equations using the least squares method. So how do you do that? You compute the pseudo inverse. Okay. So here this is your a and this is your b. So how do you find the least square solution? So x star. Okay, we'll assume that now the solution matrix x star is equal to a star b star. Okay, instead of x equals ab. Okay. Now what do you have? X star is equal to the pseudo inverse, which is a transpose a inverse times a transpose times b. Now, in order to solve it, I can left multiply again by the inverse of a transpose a inverse, which is nothing but a transpose a x star is equal to a transpose b. Right now, all I need to do is find a transpose a and a transpose. Right. So a transpose a would be 1 0 1 1 1 2 times um, this guy is 1 0 1 1 1 2, right? And x star equals, now multiply this side, a transpose is again 1 0 1 1 1 2 times b 1 2 2. Okay, now if you do this multiplication, what is the dimension? 2 cross 3, and this dimension is 3 cross 2. Okay, so I should get a 2 cross 2 matrix. Okay, and okay, I should be getting a 2 cross 2 matrix. So what I get here is 1 1 1 1 1 1, so that will be 3, and 1 plus 2 is 3, 1 plus 2 is 3, 1 plus 4 is 5. That's correct, right?
Yes.
Yeah. Okay. Times A star B star is equal to, uh, so this is 2 cross 3, and this is 1 cross 3 cross 1. So I should get a 2 cross 1 matrix. Good. So this will be 1 plus 2, which is 5, and this should be 2 plus 4, which is 6. Okay,
Yes.
good. Now, now I have a bunch of linear equations. Uh, I'll just simply do one round of Gaussian elimination, and that is R2 equals R2 minus R1, which will give me 3302 A star B star equals, um, 6 minus 5 is 1. No? So, yeah, okay, good. So I'll just copy this part. Okay, and paste it here, and which implies that 2b star equals 1. So b star is equal to 1 by 2. Now, which means that 3a star plus 3 by 2 is equal to 5. So a star equals 1 by 3, 5 minus 3 by
7/6.
2. 7 by 6? Huh. 7 by 6. Correct. 7 by 6 star. So what do you have? We have that y equals, 1 by 3 plus 1 by 2 x is the best fit. In terms of Euclidean distance, you cannot get a better line than this.
Right. Yes.
Okay. So, and this is your answer. And you can even measure how good this is by actually calculating the norm and so on. But in general, this will suffice.
So what if we have been given a matrix,
Uh,
I mean, having many rows and then many columns.
uh,
Like say, if I have a matrix of dimensions, say 10,000 into 10,000, and because 10,000 will be too much, I guess. Say, even if I take the value of the A is equal to 100 by 100, assuming that there are 100 number of the features available,
yeah.
and which we want to go for the regression kind of a thing. So
Uh,
how complex this least square method is? So complexity wise, I mean execution
Complexity
time wise,
wise,
how complex is this?
let's try to find that out. So what you are saying is, if I have an n cross n matrix, sorry, not n cross n matrix, n uh,
So I have been given say n number of the features
n
and
points
endpoints. It's endpoints, right? That will
of
be
dimension m. Is that fine? N points of dimension m. So it's like, first point is like, a1, a2, a11, a2, a12, and so on till a1m. This is the first point, and it goes on till I have a point a n1, a n2, a nm. Right?
yes,
So these many points are given to you. Now you want to find the least square solution. Firstly, you need to get this matrix A, coefficient matrix A, right? Oh, by the way, now it's no more talking about a line that fits through it. It should be a plane that fits through
right,
it,
yes,
right? Because now you have a dimension m. If the dimension is 2, then you have a line that fits through it. Okay, so dimension m. So now, so you, so this,
rather a hyperplane, yeah,
Rather,
Rather a hyperplane. I mean, we are
hyperplane.
looking
That's
for.
right. A hyperplane that fits through it all. And so these values will so a hyperplane um, in higher dimensions, right? Okay. Okay, so you'll have more factors here. So you'll have like a plus b x1 plus c x2 plus d x3 and so on, right? Or rather, let's say um, I've already used a here, no? Okay, so let's change that value to alpha. Okay, alpha 1, alpha 2, alpha 3, alpha 2 here, sorry, alpha 1 here, alpha 0 here, and so on till how many alphas will be there? Um, the alphas will be m dot alpha m xm. Okay, so this will be m tall, and a matrix is will be accordingly changed now. The matrix computation will be a bit more complex than this. That's what I believe, because not now it's not simply a plus b and so on, right? The coefficient of a is 1, but what about the others? Oh, no, no, no. Okay, that is still straightforward because it's just depending on the points. Okay, great. So this guy will still be n cross m. Okay,
Yes.
and this guy will, okay, this computation is not taken into account, but it is still n dimensional. Okay, this is m plus 1, n plus 1. Okay, now next is just matrix multiplication of n cross m matrix, m cross m matrices or m cross n matrices and so on, right? So let's just assume that suppose m is order n. Okay,
Yes.
then matrix multiplication will take some
N cube.
um, yeah, at most n cube time. In the worst case, I think the best you can do is
2 point
2.7.
2.37.
Yeah,
2.37 is the state of
2.37.
the art.
So let's just, yeah, still say n cube only.
Yes.
Okay, so this, oh, but we are not solving this yet. We are just putting it in this form. Now here we'll take n cube. Here also we'll take at most n cube, right? And get this form. So until here we are getting order n cube time only.
Yes.
And Gaussian elimination. Oh, by the way, what is the complexity of Gaussian elimination?
Uh, this because Gaussian elimination is a way wherein we are performing the row operations.
Huh.
But then I don't know how does a software I
Huh.
mean solve the linear equations even if through Gaussians or use some method to compute the inverse, because inverse seems to be more computationally I mean feasible kind of the thing, and
Oh,
this
no, 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 no. Inverse is computationally very um, task taxing
yeah,
to compute, because see, inverse is equal to 1 by adjoint of the determinant, and determinant computation is something that is not easy.
determinant is not easy, right? But then this determinant I mean we have some algorithm to compute this in the polynomial time determinant, to compute the determinant of a large matrix. But even if
Huh.
I mean to say that Gaussian elimination probably require more wisdom. I mean human wisdom kind of the thing, that which row
But
should be.
yeah, that is the misconception. But Gaussian elimination is very algorithmic, actually.
Okay.
But yeah, yeah, I agree that it seems like you need an intuition to do it. No, it
Yes.
seems like you need an intuition to do it. But if the algorithm, because we always try to simplify things, but the computer is able to perform very complex calculation, floating point calculations, and so on. So all it needs to do is, like, if this is the case, A21, A22, A23, A13, A31, A32, A33 is regardless, because we always try to simplify, we try to hack our way through it. Computer does not need to do that. All it needs to do is do R2, in R2, do R2 minus R 1 by A11.
Yes.
Okay. A21 times R1 by A11. And that will automatically make the zero.
Right. Right. Yes. Right.
And so it will just do the sequence of operations. So try it out and think about it. Gaussian elimination takes roughly order of n cube time.
Okay.
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 So because try to approximate what the number of elements in the lower triangle will be. Okay. Uh, Now that you have that, suppose order n, then at this point you'll do Gaussian elimination only. Gaussian elimination, even uh, I mean, practically you use Gaussian elimination. Okay.
Okay.
That is one of the most. I mean, there are other more efficient methods, of course, but Gaussian elimination is still a very standard and efficient method to do solve system of linear equations. Okay, and this takes order of n cube time again. So roughly the least square method should take the roughly the
Couple of
time should be order of n cube.
Yeah. I ask this question because then over the square least square method. I mean,
Hmm.
in the modern machine learning or the deep learning stuff, people prefer the gradient descent method. I mean, calculating the gradients
Right.
over. I mean, solving the things through linear algebra.
That's right.
So there might be some reason behind that the gradients are considered to be superior than the linear algebra thing, or probably linear algebra thing is more algorithmic, and then gradients can be approximated to the greater extent, kind of the thing. We can
Ah,
skip some of the data points, and then we can find, okay, in which direction we need to move to minimize the things. I mean,
yeah, yeah.
basically, yeah, that stuff.
See, I
Uh,
think okay, I'm not an AI guy, so I won't be able to give you the correct solution probably. But um, the way I see it, in order to perform least squares method, you need all the data already,
yes, yes,
right? And you just have a huge matrix of data, and then you just pass it through that and get the best fit line. And but in the case of your gradient descent algorithms, you are not you are it's more like instead of having the entire truth table, it's just like having access to a function. You get it?
yes.
So
You're right.
so you
Yeah.
evaluate the function and then try to get closer and closer. Okay.
Yes, yes, yes. Right,
So
right. That's
that
true. That's true.
that yeah, that is a difference that I see in the two approaches. That in one case you are given a function, in the other case you are given a set of data points. So I think if you are already given a set of data points, then the most efficient way to do it would be go through this process of least squares, maybe, or maybe there's a more efficient way of data fitting, like regression and so on. And I feel like if it's not clear to you and you are trying to do an what is called this um, if you're trying to do an on the spot learning, right, across you're trying to learn the function that you have, then you can't expect to get all the data points.
True, true.
So then probably that is a use case. But yeah, I think you should independently Google also, because
Yes,
I'm
yes,
not a reliable source for this.
yes. Thank you so much. Thanks.
Yeah.
So
Okay.
which topic shall be covered in the next session? Next session would be on Wednesday or on some other, sorry, Tuesday
No,
or on
yeah, it'll be on Tuesday as usual.
Tuesday.
Okay.
Perfect. Yeah.
So I think we'll have two sessions left. Yeah, this time we won't have an extra session. Okay.
Okay. Okay.
So the 12th session will be the final session.
Okay.
And next, yeah, I am also not sure. I need to look into what the contents are. Probably we'll be doing um, eigenvalues, something deeper on eigenvalues. That's what I think.
Thank you
Okay.
so much.
Okay then. Thank you.
Bye bye.
Okay. Bye. Take care.